What's going on, YouTube? I'm Rob.
I'm Bert.
Welcome back to the rabbit hole. Today we're going to be going over black holes,
White holes,
and quasars.
Oh yes, all the singularities, all the scary shit.
It's about to drop down a couple dimensions for sure. So
Yep. Get ready. Here we go.
what do you think on how much do you know about black holes? First off,
Oh, I know they're fucking huge and terrifying. I know that you can't see them. You can only see the light distortion around them that they produce from the gravitational influence. And I know that if you get a little too close, you're probably never gonna get out.
yeah. Well, actually, the event horizon around one. Once you pass it, there's no physical way you can stop. Like it can even suck in light. Once the light passes the event horizon, even that can't get out, and it's moving at the speed of light. So like you'll never get out of it.
Yeah. But what if you move faster than the speed of light?
I mean, nothing that we know of is faster than the speed of light.
Right.
So it's like,
Yeah.
is it possible?
Probably not gonna happen.
No, absolutely not. But as far as black holes go, like it's hard to think about because there's no density and there's no mass. It's just one singularity that's so high gravity. It has such a high gravitational field with electromagnetic field as well. It's just hard to wrap your head around.
Yeah.
Because like the sun, like you can kind of imagine the size,
Right.
not really.
It's like
but,
huge.
You can define what it's made of.
Right.
Like the black hole, it's kind of weird because like, what the hell is it made of?
Yeah, it's just
mostly
kinda,
antimatter is what a lot of people are saying.
Yeah, it's kind of just like this, like a pure gravitational well.
Yeah.
Like you know when they say that Earth is a gravity well, and like every kind of bodily mass that has a lot of mass has a gravitational well.
Right.
And every planet or anything that has some pull has an escape velocity.
Right.
Well, obviously a black hole's escape velocity would be higher than the speed of light because light can't escape.
Yeah. But what about a white hole?
So, explain to me again what a white hole is.
So as far as I can understand it, a white hole is essentially a singularity that occurs inside of a black hole.
Yeah.
So it's a singularity inside of a singularity. Essentially, it does the complete opposite. It's like a big bang.
Right.
Instead of constantly sucking in stuff and like collecting stuff, it's just it's basically implodes on itself and explodes.
Right. But so how would it get to that point? Because I know Hawking radiation. Stephen Hawking, before he died, won the Nobel Prize for Hawking radiation.
Yeah.
And he saw that over time, black holes actually do emit radiation from their poles, and they evaporate essentially.
Yeah.
So how would a black hole get to the point where it turns into a white hole or so-called Big Bang?
Let me go with that before you.
Okay.
We're already inside of a black hole.
All right, you're scaring me.
Because it's
You're scaring me.
Listen,
Don't do that.
listen.
Don't do that. You're scaring me.
Listen, because black holes have no end, really.
Right.
They constantly suck stuff in.
Yeah.
How do we know that we've already passed through one, and since the universe is ever expanding, that's the supermassive black hole?
Because I think no, obviously not, because we have consciousness,
What if the Big Bang?
and consciousness would not exist inside a black hole. Okay, the
Right, but
amount of gravitation.
I'm talking about like we've been in the black hole for billions of years. Think of the Big Bang as us passing through the event horizon, extremely chaotic. Then on the inside, obviously, there's some place to settle. It settles down.
So what? Bigger than the observable universe, or just the observable universe is kind of like a big bubble, and that bubble is actually the singularity of a black hole, and so that's where we could start talking about string theory, and which I don't really understand that much.
String theory is extremely complicated.
But I know the multiverse. I like the multiverse theory.
Yeah.
I like the multiverse theory. The fact that
I've also heard the theory that like black holes are like not really black holes. They're actually just like portals, 2 different dimensions or 2 different universes.
Well, since we're on the fact of singularities, what do you think about Schrodinger's cat? And so, first we were talking about the scale of the big, like black holes. So let's talk about the scale of the small real quick. So, like down at the atomic level, we know that we can't even see things like electrons. Right. We know that they're there because they produce a charge. We know that they have spin, but for some reason we can't see them. You cannot point to an electron. And the reason for that being is because what's called the there's a wave function is what they call it. Now I can't really explain to you what a wave function is truly, but they say that the wave function is something like this when we're talking about
well, let's look up wave function.
Yeah, not when we're talking about Einstein's theory of relativity, and what's the science of the really small?
Quantum.
Yeah, so quantum physics is what I was trying to say. When we're talking about quantum physics, they say that there's a wave function associated with a particle. Right. So the act of me, say, trying to look down to one atom on this table. You can't because the atoms are there. We know that they're there, and we know that we can't look at them because the act of you looking at them is indeed like a physical measurement, just as much as me putting up a ruler to it.
Right.
On the quantum level, you looking at it, that interaction is physically enough to change its state. It collapses what they call the wave function, which is the normal way that it would be if it was not being acted upon.
Right.
You looking at it collapses the wave function, and they say that you will never be able to measure where that is because of that. Right. So an easier way to think of that, I heard Neil deGrasse Tyson talk about this one. He said, imagine having at a Thanksgiving dinner the wishbone.
Right.
And you grab half of it, I grab half of it, we break it in half.
Right.
Neither one of us looks at the piece that's in our hand. You stay here on Earth, I go over to Andromeda. Right. Like the next galaxy over. I go way the hell over there. As soon as I open my hand and I look at this, I've now measured it. So faster than the speed of light.
Right.
I now know that information came to me faster than the speed of light because I opened my hand over in Andromeda. You're way over here, which is hundreds of thousands of light years away.
Right.
That information of me seeing how big my wishbone is, either you got the big piece or I got the little piece, or I got the big piece and you got the little piece. Right. That information traveled to me faster than the speed of light. That's quantum physics.
Holy shit.
Yes. And so that's more of a physical way to understand it. That's what kind of made me understand it a little bit more. I said, okay, that makes sense. But me opening my hand and looking at it would be collapsing the wave function of the wishbone.
Right.
Right? So now I know if I have the small and you have the big, or vice versa, and you would know the same. But,
yeah. So almost looks like a standard like bell curve if you were doing like a distribution graph.
Yeah.
Yeah. Oh yeah. I studied a little bit of this in physics.
When you look at it, it kind of collapses into a singularity.
Well, that's what they say right here. Is like a wave function of quantum physics is a mathematical description of quantum state inside of an isolated quantum system. Wave function is a complex valued probability amplitude, and the probabilities for the possible results of measurements made on the system that can be derived from it.
Right, so in other words, that's pretty much restating what I just said.
Right.
As soon as you measure it, it's going to change on you. It's going to collapse.
It's like, dude, oh my god, you're like 5-minute spiel, like completely going into Andromeda. Mm-hmm. And then you're like, basically.
Yeah. Well, not minus the Andromeda part, but the collapsing of the wave function, like the measurement of it is what makes it collapse. And it kind of shows you because quantum physics says that when we break the wishbone, I have the big piece and the small piece, and you have the big piece and the small piece. Right. And until we look at it, only then will I have either one the big piece or one the small piece, because I cannot exist in two different realities at once. So they split. And this splitting keeps happening like billions of times a second, and that's what they call the multiverse. But you're pretty much traveling through only one path, and the consciousness that you see is going to be on that path only.
Right here, collapse wave function.
Right. So that's pretty much, they have an electron, they have a slit in a piece of paper, and then they have a description of the wave function with it not being detected, and they have a description of it being detected. So the wave function is nice and flowing with the frequency and the.
But the minute an electron goes near it.
Right. Well. The minute an electron detector looks for the electron, it collapses.
No shit.
Because the act of trying to measure it is what makes it collapse. Do you see what I'm saying?
Yeah.
Like you just looking at it is
sends
the same.
Off electrons.
It puts enough pressure on that atom to change its state.
No shit.
Instantly, faster than the speed of light, because quantum physics is faster than the speed of light. And Einstein's theory of relativity and special relativity is the theory of the really big, and his theory of the really small, which involves quantum physics. That would be special relativity. Relativity is like, relativity leaves us off at a black hole.
Right.
It doesn't know what happens at the center of a black hole, which is why it's called a singularity.
Right. There's not one single thing like it.
Right. But the thought of a white hole is
insane.
Yeah.
Right? I read that. Insane. I read on that today.
Yep.
And I was just thinking like, oh wow, holy shit. So maybe
it's terrifying.
Maybe the Big Bang was a white hole.
Maybe. And maybe they happen all the time.
Yeah, because that goes into multi-universal theory. Mm-hmm. But the thing is, where would they happen? Because if another white hole happened in our universe, would kill us. So the implication of there is a white hole also implies that there are multiple universes.
Right. Yeah.
You know what I mean?
Mm-hmm. White hole is essentially the birth of
a universe.
Yeah. Of one of the multiverses.
Right.
Yeah. So a universe. Right.
Right. That's insane.
Shit's crazy. Yeah.
That's insane.
I can't think.
That's
my head hurts.
Yeah. I mean, like
oh
I think of it as like almost like there's like individual kind of like spots.
Mm-hmm.
You know what I mean? Obviously, our universe, like, let's say, takes up this wedge. But if we have another white hole and it makes something this size of this wedge, it's going to take out everything here. So it goes over here. It goes over here. Every single little part of the puzzle. And who's to say that there's something that's bigger than that?
Well, here. Let me ask you this: what is Schrodinger's cat? Do you remember that experiment and what he was trying to do? Because I kind of do, but I don't.
I can't. But
it's hard to explain. I have a really hard time explaining his.
I remember it's like
outcome,
something
like
about a cat in a box, but it's like it's a theoretical question.
Yeah. So
it's a thought experiment.
Yeah.
Right here.
Let's Wikipedia. Because Wikipedia is very trustful.
Yeah.
Very trustful.
This the sources must be in APA format.
Yeah.
No Wikipedia, and like all caps. No Wikipedia allowed. Like, yeah, it's better than most books. Schrödinger's cat is a thought experiment, sometimes described as a paradox, devised by Austrian-Irish physicist Erwin Schrödinger. Schrödinger.
Yeah.
In 1935. During the course of discussions with Albert Einstein. It's illustrated the way he saw was a problem of Copenhagen interpretation. What the hell does that say? Interpretation?
Copenhagen interpretation of quantum mechanics.
Interpretation.
The scenario presents a hypothetical cat that may be simultaneously both dead and alive. A state known as quantum superposition. So that's what I was saying when I said I have both the big piece and the little piece of the wishbone.
Right.
The wishbone, until our eyes act upon it and we see which piece we broke off.
Oh, right here.
it's in a superposition, and we have both essentially.
This is the one that he wrote. This is what he actually wrote. It says, one can even set up quite ridiculous cases. A cat is penned up in a steel chamber along with the following device, which must be secured against direct interference by the cat. In a Geiger counter, there is a tiny bit of radioactive substance, so small that perhaps in the course of 1 hour the atom decays, but also with equal probability, perhaps none. If it happens, the counter tube discharges through a relay, releases a hammer that shatters a small flask of hydrocyanic acid. If one has left the entire system to itself for an hour, one would say that the cat still lives, if meanwhile no atom has decayed. The first atomic decay would have poisoned it. The psi function of the entire system would express this by having it in living and dead cat, pardon the expression, mixed or smeared out in equal parts. Dude, so this is, even though it's a thought experiment, this is a very high level thought experiment.
Yeah, so it's pretty much what it's once again just it's trying to give different examples of the wishbone.
Right.
The wishbone is the easiest to think of.
Right.
Like the Schrodinger's cat thought experiment is a good one because it gets you thinking about superposition and the fact that things can be in two states at the same time until acted upon. And when you act upon them, aka look at it and try and measure where and what it is in space and time.
Right.
Only then does its wave function collapse and it goes one of two ways. Or one of many ways, however many possibilities. If we're playing 52 cards,
right,
we there's a lot of possibilities. If we're rolling 2 dice, there's less possibilities.
Right.
But you see what I mean? This is
as
how
far as wave functions go.
Right. That's kind of going in depth, but too much further than that, and my brain starts hurting.
Dude, yeah, we're getting the gears going. We're actually going into very deep stuff right now.
Yeah. It's hurting my head. A lot.
Me too. My glasses I have to get checked. But I have my surgery in January.
Yeah. Yeah, you're getting like a type of LASIK or something, right?
Yeah, it's something like that. I can't get official LASIK, but basically LASIK. Mm-hmm. Dude, quasars. We almost forgot.
Oh yeah.
You know what quasars are, right?
Explain it to me.
You've heard of a gamma ray burst?
Yep.
That's a quasar.
Right.
So essentially what happens is sometimes black holes emit these basically obviously the black hole, think of it right here, and then you have the disk of stars that's sucking in right here. Mm-hmm. So a quasar is essentially a gamma ray burst of radiation that shoots out at both poles, negative the positive pole. Mm-hmm. And it's essentially as gross as it sounds, it's like a black hole, burping, essentially. But it shoots out this super powerful gamma ray
plasma
burst.
jet, yeah.
That travels, extremely fast. I wouldn't say
it's almost the speed of light. Probably.
Basically, it's all it is radiation, so it's probably 95% the speed of light.
Yeah.
But it's extremely dangerous. Mm-hmm. If this hit anywhere near our solar system, we would be dead as shit.
Oh yeah.
It doesn't have to actually directly hit us. The radiation alone would just destroy anything.
So how is a quasar made? Is a quasar the remnants of a black hole after it's evaporated?
No,
is it a massive star that has just collapsed and collapsed?
Right here, a massive and extremely remote celestial object emitting exceptionally rare amounts of energy and typically having a star-like image in a telescope. It was suggested that quasars contain massive black holes and may represent a stage in the evolution of some galaxies.
Mm-hmm. So it is a black hole then, essentially, emitting light from its poles.
Yeah, basically.
Okay, gotcha.
Here, we'll go to the old Wikipedia. But yeah, dude, they're insanely crazy. There's only been a few that have been recorded on a camera, and just to watch it just from such a distance, it's so massive.
Yeah.
Massive, galaxy massive.
Mm-hmm.
Right here. Extremely luminous active galactic nucleus, which in a supermassive black hole with mass ranging from millions to billions of times the mass of the sun, surrounded by gaseous
accretion disk.
Accretion disk.
That's that swirling hot gas that you
yeah,
see around it, like constantly funneling in.
As the gas in the disk falls towards the black hole, energy is released in the form of electromagnetic radiation, which can be observed across the electromagnetic spectrum. The power radiated by quasars is enormous. The most powerful quasars have luminosities thousands of times greater than the galaxy, such as the Milky Way. So it's
That's
like
insane.
It's like basically like this super powerful, super focused beam of energy that just shoots through galaxies.
That's wild.
It's evil. Especially thinking of the size of that. That's the size of the galaxy. So this has got to be what? How wide is the Milky Way galaxy?
100,000 light years.
So this is probably 2,000 or 3,000 light years across, containing all of that.
Yeah, that's insane.
Yeah, and it's basically a delete button.
Yeah.
It's literally a universal delete button.
Yeah.
But they have some photos of them, and they're like, look at this. How it goes across, because they're always going to shine like this. You know what I mean? When one that goes across, that's pretty crazy.
It's so crazy to think that we've just started.
This one's
like within the past 100 years.
Yeah.
Like humans have been on Earth for, we think, what, hundreds of thousands, if not over 1 million years.
I would say like close to like 500,000, 2 million.
Right. Okay. So we've been here a long fucking time. Then look it up. Look that up. How long have humans been walking upright and could be called humans? I guess.
But it's taken us so long to get to here. But now we're accelerating so fast in how much we research.
Yeah. So just in the past 100 years, in the past human lifetime, one human lifetime ago, we started looking up, or started looking up and started really understanding what we were seeing. Like, before that people had the sciences and they knew that there were planets and they knew all this stuff, but right here, we're getting to the point where we're looking at, superposition of electrons and superposition of things and quantum mechanics and trying to understand singularities of black holes and whatnot. And obviously 50, 60 years ago, not even 100, people weren't thinking about shit like that.
No.
And not nearly as advanced as that.
Well, it says like right here, it says the first anatomically modern humans are from the Paleolithic, like 200,000 years ago, but then it says here, they were making crude stone tools 2.5 million years ago.
Yeah.
So maybe like modern, they think like, modern bone structure. But if you're talking about like the start of humanity, where they're starting to use tools and starting to actually, the biggest evolutionary trait right here.
Right.
Opposable thumb.
Yeah, seriously.
Dude, it literally is. So, like, look it up. It really is.
Seriously.
That in the size of our brains compared to our body. But it's cool because you look at it, you could start at 2.5 million years ago, but really, biologically, it's like 200,000. But now, within the last 400 years, Galileo was like 1610s, right?
I'm not sure. I think it was,
or was around. I think it was like
16 or 1700s. I can't remember.
Right. So like we'll say like 300 to 400 years.
Yeah.
Out of that 2.5 million years, only the past 300 to 400 years, we've actually been studying the stars.
Which is a blink of an eye.
Intently.
Not even a blink of an eye.
Recording mathematical equations on how to solve that, and like physically recording it. So that's absolutely insane.
Right. Which in the 13.8 billion years that has been the universe, we've been looking up and understanding for maybe a couple hundred. And we're just now starting to really see. So
it's like not even
just to check your ego real quick. You don't know shit. We're just advanced apes, man. Basically, we don't know shit.
Basically, if you think about it as like, if the whole universe existed as a day, our understanding of it
is less than a second.
Like less than a millisecond.
Yeah.
Dude. Think about it. Like the universe is like
just.
Was it 13.5 billion
13.8 billion years.
13.8 billion years old. We've only known about this kind of stuff for 300 to 400. It's not even a millisecond. It's so compressed along the timeline. I think so too. I think this was good. I think we went down some pretty deep rabbit holes.
Time to pull ourselves back out.
yeah, get the rope.
yeah.
Alrighty.
Thanks for watching.
We'll see you next time.